Hello, and welcome to Differential Equations. This is Lecture 4, Existence and Uniqueness Theorem. Last time, we talked about slope fields and using them to get ideas of the behavior of solution curves, even when you don't know what the actual solution is, when you don't have an explicit formula. This time, when can we guarantee that a first-order initial value problem has a solution? When can we guarantee that it has only one solution? Okay, so we'll jump straight in with the answer. Here's the theorem. Our existence and uniqueness theorem. So consider the initial value problem. Y by dt is equal to f of y and t. Y of t0 is y naught. Okay, so there's two parts. For the first part, we require that f is continuous in a neighborhood of the initial condition point. Then we conclude that a solution exists in some rectangle of the form t minus t naught in absolute value less than delta, y minus y naught in absolute value less than epsilon. Right, so there's this neighborhood, this rectangle that's perhaps really small, but we know that in this rectangle, there is a solution curve to the differential equation. Right? Then part two, we need to strengthen our hypotheses to conclude uniqueness. So here we'll say, if in addition, the derivative of f with respect to y is continuous in a neighborhood of the point, given by the initial condition, then the solution in this small rectangle is unique. Okay, so this theorem was proven by Picard, who we mentioned last time, Emile Picard, under the stronger assumption. So if you assume that the derivative is continuous, then he proves both parts of the theorem. The removal of that assumption in part one, so the fact that we only need that f is continuous in order to get existence, that was proven by an Italian mathematician known as Giuseppe Peano. You've probably heard of Peano because of the Peano axioms for the natural numbers. You may also have heard of Peano because he's the first person to have constructed a space-filling curve. So this is a a curve, so it's a function that takes the interval, the unit interval, and maps it onto the unit square, right? So it's a one-dimensional interval, and it fills up a two-dimensional square, and it does it continuously. Right, so that Peano, he's the one who proved this existence part with the weaker hypothesis. Okay, let's start with an example that we've already come across. So recall that the initial value problem, dy by dt equals y to the 1/3, with initial condition y of 0 equal to 0, has two solutions, right? If you take the function that's identically equal to 0, that satisfies both this equation and this initial condition. And if you take the function 2/3 t raised to the 3/2, then this also satisfies both this equation and this initial condition, right? So this is a situation where the theorem fails, right? Or the theorem's conclusions don't hold. So let's notice here our function f of y comma t is y to the 1/3, right? Which is continuous in a neighborhood of the point 0, 0. But if we take the derivative of f with respect to y, we get 1/3 y to the minus 2/3. And this is not continuous. It's not even defined at 0, and it's not continuous in a neighborhood of 0, 0. So in this case, this function is continuous, so it does satisfy the hypotheses of part 1, which is fine. That says that a solution exists, but the derivative is not continuous, so it doesn't satisfy this additional hypothesis for part 2, and so it's no contradiction that the conclusion of part 2 doesn't hold. Right? Notice that the theorem doesn't say anything about what happens when this doesn't hold. So here there are multiple solutions, but if there had been only one solution, that would be fine too. It doesn't contradict the theorem. Let's do another example. So let's consider dy by dt is y minus 5 times natural log of the absolute value of y minus 5 plus t, y of 0 equals 5. Okay, so here, our function f of y comma t is y minus 5 times the natural log, the absolute value of y minus 5 plus t. And this function is continuous in a neighborhood of the point 0, 5, right? So notice, of course, this logarithm has a singularity when y is equal to 5, but this term that's multiplying it is strong enough to defeat that singularity, and so this actually is continuous when y is equal to 5. So the theorem guarantees the existence of a solution for t sufficiently close to 0. However, we take the derivative of f with respect to y, we get 1 plus natural log of absolute value of y minus 5. And this is not continuous. In the neighborhood of this point, t equal to 0, y equal to 5. So the theorem does not guarantee uniqueness. Right? So it's not continuous, so the theorem does not guarantee uniqueness, right? But that's all the theorem does. It does not guarantee uniqueness. The theorem doesn't claim that there are multiple solutions. Notice that if the initial condition different, for example, let's say you had y of 0 equal to 1, then both parts of the theorem would apply. Right? So the existence uniqueness theorem requires more than the equation. You also need to take into account the initial condition to see whether or not the theorem applies. Okay. The way the theorem is proven is using an iteration scheme. Called Picard iteration. Right? Starting with the problem, right, t is equal to f of y comma t, and an initial condition, y of t naught is y naught. We construct a sequence of functions y sub n of t that get closer and closer to solving the differential equation. The initial guess, right, y sub 0 of t is just the constant function satisfying the initial condition. Right, so y sub 0 of t is just always equal to y sub 0. For the next guess, we solve the modified initial value problem. Right? So dy dt equal to, and instead of having f of y comma t, we're just going to put f of y naught of t comma t, right? With the same initial condition, y of t naught is equal to y naught. Okay, so notice that now the right-hand side doesn't depend on y, right? Because we've substituted in y naught of t, which is just a constant, y naught. So that means that this is a really easy equation. You solve it just by integrating both sides. So let's call that y1 of t. So this would be the constant y naught plus the integral from t naught to t of f of y naught of s, comma s, ds. And continuing in this way, we define y sub n of t to be the constant y naught plus the integral from t naught to t f of y sub n minus 1 of s, comma s, ds. Right, so in this way, we've defined a sequence of functions, and the proof of the theorem then comes down to proving that this sequence converges. Okay, so this method works great as a theoretical tool. On the other hand, it is a terrible way of actually solving a differential equation, even approximately. In practice. There are other methods based, for example, on perturbation methods that give highly accurate approximations with a lot less work. Okay, so, but again, this method works great as a theoretical tool. It's just not how you'd want to solve an equation in practice. Most of the time, some equations are simple enough that you can carry this out explicitly and solve the equation. It's not just that the equation is simple enough, it's that it lends itself to this computation. So here's what I mean. For some very easy equations, we can carry out the iteration explicitly. Here's an example. Let's consider dy dt is equal to 2t times 1 plus y, right? So a nice separable equation with initial condition y of 0 equals 0. Okay, so our first guess, y0 of t, would satisfy the initial condition, so it would just be 0. That means y1 of t would be 0 plus the integral from 0 to t of this right-hand side, but instead of y, we're going to put our first guess, 0, right? So that means we would have 2s times 1 plus 0 ds, right? Okay, perfect. So we're just integrating 2s with respect to s, so that's s squared over 2 times 2, s squared, evaluated at t and 0, we just end up with t squared, right? So that's our next guess, y1. So then y2 of t would be 0 plus the integral from 0 to t of, so I'm going to take this right-hand side, and I'm just going to replace the y with our previous guess, right? So it's going to be 2s times 1 plus s squared, right? So, okay, we can work that out. We end up with t squared plus 1/2 t to the 4th. Okay, let's keep going. Y sub 3 would be 0 plus the integral from 0 to t. And now we're going to put in this right-hand side. And instead of y, we will put y2. So that becomes 2s times 1 plus s squared plus 1/2 s to the 4th ds. Right, and that integrates to t squared plus 1/2 t to the 4th plus 1/6 t to the 6th. Right, so you can see why this example works out easily, because at every step, what we had before remains, and we're just adding an extra term. So if you keep going like this, the nth term would be 0 plus the integral of 2s times 1 plus your previous guess. And this would work out to t squared plus 1/2 t to the 4th plus dot, dot, dot. And then you'd be adding 1 over n factorial t to the 2n. Okay? Okay, so that's the nth term in the sequence. Going from that to some sort of explicit solution, well, in this case, we can do it, but only because this is a really simple series, and we can just recognize it. So recall that e to the t has Taylor expansion, right, given by the everywhere convergent series, 1 plus t plus 1/2 t squared plus dot, dot, dot plus t to the n over n factorial plus dot, dot, dot. Right, so now if we stare at the series we have and the series for e to the t, so we recognize that y sub n of t is going to converge to e to the t squared minus 1. Right, just because if you plug in t squared here, you would get this series, except you're missing that initial 1. Okay, great. So in this case, we can recognize that. Now, of course, it's really easy to check whether or not that works. Notice that if y of t is equal to e to the t squared minus 1, then dy dt would be equal to, well, d by dt of e to the t squared minus 1. So that would be 2t e to the t squared, right? But e to the t squared from over here is just y plus 1. And if we evaluate it at 0, we get e to the 0 minus 1, so it's 0. Right, so this is indeed a solution, but of course really the solution, because we know from our existence and uniqueness theorem that there's only one. Okay, so great. This case worked out really nicely, and we were able to recognize what the solution was. That's not how it usually goes, though. So here's another example. Let's consider uy dt equals t squared plus y squared with the initial condition y of 0 equals 1. Right, so here, our initial guess, y sub 0 of t, would just be identically equal to 1. And then for n greater than 0, y sub n of t would be equal to 1 plus the integral from 0 to t, s squared plus y n minus 1 of s squared ds, right? Because you just take your previous guess and you plug that in here instead of y. Okay, in this case, y1 of t would be 1 plus t plus 1/3 t cubed. y2 of t would be 1 plus t squared plus 2/3 t cubed plus 1/6 t to the 4th plus 2 over 15 t to the 5 is 1 over 63 t to the 7. y3 of t would be 1 plus t squared plus 4/3 t cubed 5/6 t to the 4th, 8 over 15 t to the 5, 29 over 60 t to the 6, 47 over 315 t to the 7th, blah, 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 until 1 over 59535 t to the 15. Right? So in this case, the pattern for the coefficients is not clear. So it would be hard to guess the solution like we did in the previous example. And this is what you would expect this method to look like in general. It's it's going to be very rare that you end up with something really nice that you can recognize and just write down what it's converging to. Usually you're going to get some sort of a mess, and it's only because of the abstract theory that you know that this is converging at all, right? It's not clear from looking at it. Let's say a little more about this abstract theory, right? So how does one know? Or even better, how does one show? that the sequence converges. Right? Not in this particular example, but in general. Well, we're not going to prove this, but let me just sketch how the argument goes. Consider the map, let's call it capital T, that goes from functions to functions. And we want the one that takes a function y to the function t of y, right? So this is a function, which means that I should evaluate it at a point and then get back a number. So let's say you evaluate this at the point t, and here's the number you get back. You get back y naught plus the integral from y naught to t of f of y of s, comma s ds. Right? So the Picard sequence right, in terms of this map capital T is given by, well, you start with y naught, then y1 is just capital T of y naught, right? Because how we get y1 is exactly this right-hand side where we plug in y naught instead of y, right? Then y2 would be T of y1, right? But y1 was just T of y naught. So altogether, this is equal to T applied twice to y naught, right? Then y3 would be T of y2, right? But y2 is T applied twice to y naught. So y3 is T applied 3 times to y naught, right? And so on. The nth term in our Picard sequence is the effect of applying capital T n times to y naught. Okay, then what one shows is that there is some appropriate notion of size of a function. Right? Which I'll denote like this. So 2 vertical bars. It's pronounced norm. And that if you measure size with respect to this norm, that t reduces distances. So the size of the distance between t of f and t of g is less than or equal to some constant times the distance between f and g. And this constant, crucially, is strictly less than 1. Right? When you have something like this, then the map T is called a contraction. Right? So that's enough to show that the sequence y sub n given by applying t n times to y naught converges. Right? And what's more, if we call the limit y sub infinity, and notice that y sub infinity, right? So this would be the limit as n goes to infinity of t to the n applied to y naught, right? That's the same as the limit as n goes to infinity of t applied to t to the n minus 1 times y naught, right? But the limit of t to the n minus 1 applied to y naught as n goes to infinity is again y infinity, right? Because if you're applying t n minus 1 times and n goes to infinity, then you're still applying t like infinitely many times to y naught. So this limit is equal to t of y infinity, right? So we say that y infinity is a fixed point of t because t just sends it to itself, right? Okay, but what does that mean? Because let's remember we have a formula for t, right? So if y sub infinity is a fixed point, then this tells us that y sub infinity of t, right, is equal to t of y sub infinity applied to t. So that's y naught plus the integral from t naught to t of f of y infinity s comma s ds, right? And this is just another way of writing that the derivative with respect to t of y infinity is equal to f of y comma t infinity, and y infinity at time 0, well, time t naught, is equal to y naught, right? That is to say, just take the derivative of this with respect to t, and you'll get this. And if you plug in t naught, well, the integral from t naught to t naught is 0, so you just get y naught, right? Just like we wanted. Right. So of course the parts we're not going to go into is defining this appropriate notion of size of a function so that t is a contraction, and then that's enough to know that it converges. But if you believe that, it converges, then what it converges to is a solution to the differential equation. Okay. Very good. So that's where the regular lecture ends. So feel free to stop watching now. What follows will not be on the homework or on the exams, but is just some historical context. Okay. This time, I want to tell you about the cycloid. Right? So the cycloid is the curve you get. Suppose you have a wheel, and on this wheel, you have a nail at the very edge of the wheel. And then you let the wheel roll forward and you keep track of what's happening to this nail, right? So it'll do something like this and then do it again, right? And so on, right? If you've ridden a bicycle with a reflector on the edge of the bicycle, say you have like a car shining its lights and you ride your bicycle in front of that, then the reflector, if it's all the way at the edge, would be precisely tracing out this curve, right? So this curve is known as a cycloid. If the radius of this is equal to a, say, so that this point at the top is at 2a, then of course this point is at 2 pi a, right? It's easy to work out equations for this curve just by keeping track of what happens, say, to x and y separately. Once the wheel has rolled an angle of theta, then x will be at a times theta minus sine theta, and y will be at a times 1 minus cosine theta. Okay, so this curve was perhaps first studied by Galileo, who apparently figured out the area under the curve in a clever way, given that this is before calculus, so he couldn't just integrate the curve. So what he ended up doing was he traced out both the cycloid and the generating circle out of sheet metal, very thin sheet metal. Then he cut them out and he weighed them. And he found that his little model of the cycloid weighed roughly 3 times as much as the circle weighed. And so he speculated that the ratio between the areas would be basically 3, although he incorrectly thought that was an approximate value. It turns out he was right. He was just more right than he knew. It's exactly 3. Okay, so he's the first one to be studying this curve, at least mathematically. But he also enters the story I want to tell you because he proposed an interesting question. Suppose you have 2 points, right? A point A and a point B. Point B is lower than point A, and you want to put a wire between them and have some sort of like bead or marble slide down the wire without friction. So Galileo asks, would the bead get there faster if instead of doing a short segment, right, a line segment is definitely the shortest distance. But Galileo asked, would it be faster if you followed like part of a circle, right? And he speculated that yes, it would be faster to follow the circle because even though you're going a longer distance, you pick up enough speed at the beginning that you're going to get to point B faster. Right? So, okay, Galileo just asked about those 2 curves, a circular arc and a straight line. Many years later, Johann Bernoulli posed what's called the Brachistochrone problem. So Brachistochrone is Greek for shortest time. So the Brachistochrone problem is the shortest time problem. So what Johann Bernoulli asked is, okay, let's say you have A and B, just like Galileo, but don't limit yourself to just looking at the straight line and a circular arc. If you're allowed to use any curve you want, what curve will get you from point A to point B in the shortest time using only gravity, right? So he posed this problem. Several people were able to solve it, including him, and his solution was by solving a separable ODE. So since we are now experts at solving separable ODEs, let's talk about how he did this. So it's interesting how he got the equation, right? So to get an equation for this curve, we start with Snell's law. Right? So Snell's law is a law in optics. It says that when light travels from one medium to another, it refracts in the following way. So let's say that here you have medium A and here you have medium B. Then if light is going, well, maybe let's call these different. So let's call this medium M1 and this medium M2, right? And you have a point A over here and a point B over here. Then light will go along one path in medium 1 and different path in medium 2, different straight line. this is what happens when light has one constant speed in medium 1 and a different constant speed in medium 2, right? Then it refracts in this way, and it refracts so that if this is angle alpha 1 and this is angle alpha 2, then sine of alpha 1 divided by v1, so v1 is the speed of light in medium m1, is the same as sine of alpha 2 divided by v2, where v2 is the speed of light in medium m2. Right? So this was a law discovered by Wilfred Snell, a Dutch scientist. It was explained by Pierre Fermat using his principle of least time. So the principle of least time says that light will always travel along the path which gets it from point A to point V in the shortest time possible. Right? So perfect. So that seems tailor-made for the Brachistochrone problem, right? We're looking for the curve of shortest time, and Fermat asserts that light will always follow the path of shortest time. So what Bernoulli did was he just wants to allow for light to be always making choice about which way to go, right? So assume that you have a medium changing continuously, and you want to know what would light do, right? So if we have now the same setup as up here, right, points A and B, and let's say this there, oh, let's move point B because I missed it. Then the situation at a point here, well, let's give ourselves a axis over here, and let's say that this distance is y, and at this point we could draw the tangent line, right? Then here we would have the angle alpha, and if we draw a parallel here, then let's call this complementary angle beta, right? So from Snell's law, we would want to study this when sine of alpha over v is some constant. Okay, now we can throw some physics at this, and conservation of energy. Conservation of energy tells us the velocity obtained by the bead at after it's gone down y. Well, its velocity is determined solely by its loss of potential energy, right? And so it has to be given by square root of 2gy. Right? On the other hand, from this figure, we see that the slope of the tangent curve is tangent of beta, so slope of tangent is tangent beta, right? But on the other hand, the slope of the tangent is the derivative of y with respect to t. So from here, we can figure out that sine of alpha, right, using a little trig, is equal to 1 over square root of 1 plus tangent squared beta, right, which is 1 over square root of 1 plus dy by dt squared. Okay, so if we combine those equations, we get that right, so over here, sine of alpha is given by this, divided by v, which is equal to this, that's equal to a constant, so that tells us that 1 over the square root of 1 plus dy dt squared times v, which is square root of 2gy. All of this equal to a constant, right? And from there, we can figure out the equation. Right? If we rewrite this as y times 1 plus dy dt squared equal to a constant, let's give that constant a name now, a, then we can solve for dy dt. We get square root of a minus y divided by y. And this is a separable differential equation, right? The differential form version would be y over a minus y square root dy is equal to dt. And you solve this by integrating both sides. So the solution would be, actually, sorry, let's make, well, that's fine. The solution would be t plus a constant equals the integral of square root of y over a minus y dy, right? This integral you can carry out using a trigonometric substitution, make y equal to a times sine squared of phi, right? So then dy would be equal to 2a sine of phi cosine phi, and you end up with the integral of 2a sine squared phi d phi, and so a over 2 times 2 phi minus sine of 2 phi. Right, since we're looking for the solution through the origin, then this constant would just be 0, and hence t of phi would be a over 2 phi minus sine of 2 phi, and y of phi is a times sine squared of phi, right, which is a over 2 times 1 minus cosine 2 phi, right? So if we set little a to be capital A over 2, and we set theta to be 2 times phi, we end up with t of theta, or let's just say t is a theta minus sine theta, and y is a 1 minus cosine theta, which is a cycloid. Right? So this Brachistochrone problem, right? Find the shortest time curve from point A to point B, right? The answer is a cycloid. So okay, wonderful. The cycloid is great because of that, but it also has another really important property that was noticed by Christian Huygens. Huygens noticed that, right, okay, so why? So Christian Huygens was really interested in making accurate clocks, right? So before we had GPS, finding where you were when you couldn't see land, when you were in the ocean, was really hard, right? So latitude, you can figure out by just keeping track of how high the sun gets in the sky. But longitude, the sun is not going to tell you. If you have really accurate star charts, you might be able to do something. But what you want to do is just keep track of how long you've been sailing, just comparing the time when the sun gets to the highest point. So when you get to solar noon, you want to know what time is it at the place you left when the sun is at noon at the place you're at. That tells you how far you've moved in east-west, right? But for that to work, you have to have really accurate clocks. So Huygens noticed that if you have a clock that works with a pendulum, then the problem for keeping track of time by the swings of a pendulum is that the time it takes a pendulum to swing depends on how far up it's gone, right? So if I swing the pendulum and it doesn't go quite as high as it did the previous swing, then it's not going to take the same amount of time to swing. And so, I'm not being as accurate as I would like keeping track of time. So Huygens wondered if there was some curve that didn't have this problem, right? You want a curve so that if the pendulum is following that curve, then every swing of the pendulum takes the same amount of time, regardless of how far up the curve the pendulum got, right? So another way of saying that is you would like to have some curve, right? So let's say again, you have a point A and point B, and let's think of it again as little beads. You'd want to know that if I put a bead here, or I put a bead here, or I put a bead here, wherever, right? Think of this as the highest point that the pendulum got on its swing. If you release the beads at the same time and let them go down using gravity, only gravity, then you want the beads to all arrive at point B at the same time, regardless of where they started on this curve, right? So Huygens called such a curve a Tautochrone. Because in Greek, Tautochrone means same time. So it's the same time curve, right? And Huygens was able to show that there is such a curve, and it is the cycloid. So not only is it the fastest curve for going from point A to point B, it also has this property that it's going to take you the same time to get there, regardless of where you start. Okay, now of course this still leaves a problem if you're constructing a clock. How in the world do you construct your clock so that the pendulum will follow a cycloid, right? So Huygens solved that too. So Huygens noticed that if you take a cycloid and then you take another copy of the same cycloid and you put your string, the pendulum, let's say something like string so that it can roll, then let this swing between these two pendulums, and it's going to, maybe I drew this too long. Right? As this swings, it rolls along this cycloid and then rolls along the other cycloid, and it traces out a cycloid, right? So, and Huygens actually built clocks like these with pendula following cycloids, right? And so it's a mathematically designed clock to keep accurate time. Okay. In practice, it turns out that this is a terrible idea because, well, it's very expensive to construct, and in practice, a small circular arc and a small cycloid arc look pretty similar. So instead of going to all of this trouble to construct a clock so the pendulum will follow a cycloid, what you can do is construct a clock where the pendulum moves very little. And if it's moving very little, it doesn't really matter whether it's following a cycloid, which is hard, or a circle, which is easy. And so that's why you end up with clocks that are really long, have really long pendulums that only get to move very little, right? Grandfather clocks, right? Because then you're not really losing a lot of accuracy by using a circle instead of a cycloid. All right, so we'll stop there and pick it up next time.